Okay, so this is section 3.2, and previously we saw that if we had a function, a scalar function, okay, maybe the temperature in your room, you could take the gradient of this thing, and this thing is a vector. So the gradient of f we saw was a vector with x component df by dx, y component df by dy, z component df by dz. And we saw that this nabla operator could be written kind of on its own, d by dx, d by dy, d by dz, okay, where it's understood that it acts on something. Okay, in this top case, it's acting on f. Okay, and before we introduced vector fields, so just previously, so these are functions that give you vectors for each point in space. So the question is, can we kind of marry this thing to act on vector functions? So here it's acting on the scalar function, maybe the temperature in the room. Can it act on vector functions? So let's see. And maybe one thing to notice, this nabla operator, this is a vector field itself. Okay, it's for every x, y, and z point, it gives you a different vector. Okay, so this vector depends on x, y, and z. So this is a vector field. Okay, so let's think about if we had two vectors, let's say a and b. A given by ax, ax, ay, and az. Okay, that's one vector, and then a different vector b, which is bx, by, bz. Okay, what can we do to those two vectors? So how can we join them? Or how can we get them to act on each other? Okay, well, there's one thing we can do. We can take the dot product, the scalar product. Okay, we can take a dot b. Okay, and this is equal to ax bx plus ay by plus az bz. Or another thing we can do is take the cross product a cross b. Okay, and if you remember how to take the cross product, okay, I always remember it in terms of taking a determinant like this. So ijk, and then we've got ax, ay, az, and we're taking the cross product with bx, by, bz. So this gives us a vector that has x component equal to ay, bz minus az, by. Okay, that's the x component. The y component is, so we cover up this middle one. And because it's the y component, the sign swap, so it's now az times bx minus ax bz. Okay, and the j component, sorry, the last component, the k component, we cover up this, and we get ax by minus ay bx. Okay, so this is another vector, okay, which we can call c if we want. Okay, and it's got components ay bz minus az by. That's the x component. The y component is this, and the z component is this. Okay, now can we think about what we can do with this nabla? Okay, and the analogous operation to 1 is called the divergence of your vector. So the divergence of A, okay, is taking the scalar product of this vector, this nabla, with A. Okay, so this is the scalar product of d by dx, d by dy, d by dz with ax, ay, az. Okay, and this equals dax by dx plus day by dy plus daz by dz. Okay, and this thing, just like before, two vectors gives you a scalar. Okay, so this is scalar results. Two vectors gives you a scalar. So scalar results. Okay, it's just a number. And analogous to the second one, we can take the curl, what's called the curl of the vector A. Okay, it's the cross product of nabla with A. And in this case, instead of ay, we've got d by dy, so it's the y component of this. So the curl of A will be given by, so this will be given by ijk, and now nabla is d by dx, d by dy, d by dz. Okay, and we've got ax, ay, az. Okay, and it's this kind of determinant. So here, where we have ay, bz, we've got the y component of nabla, which is d by dy. So it's daz by dy, okay, minus day by dz. Oops, that's the x component. Okay, and note here, it's important to have this partial derivative on the left-hand side. Okay, so we can't write ay d by dz. Okay, it's d by dz of ay. Okay, and the y component, again, we cover this up, and we've got dax by dz minus daz by dx. Okay, and the z component, we cover this up, and we've got day by dx minus dax by dy. Okay, so this is known as the curl, C-U-R-L, of A. Okay, and this is known as the divergence of A. Okay, or maybe just div A. Okay, and these are very important and useful things to work with. Okay, so this first one gives us a scalar, the second one gives us a vector. Okay, so you should be able to write down what the divergence of A is, or the curl of A. Okay, so you should be able to recall that this nabla operator takes this form, d by dx, d by dy, d by dz. And of course you should really be able to, it should be burnt into your mind how to calculate a cross product. Okay, so you're just calculating a cross product, in this case, of nabla with A, or in this case, a dot product. Okay, so you can just treat it like normal vectors that you saw with Kathy. Okay, so let's look at examples to see what these things mean. But basically, the divergence of A tells you about the presence of sources or sinks of something. And the curl of A tells you about whether rotations are present or not. Okay, so let's have an example to make that a bit more concrete. Okay, so let's look at some examples. Let's think about the function f of x, y, z equals r. Okay, some radial vector magnitude. We know this is just the square root of x squared plus y squared plus z squared. Okay, we want to find what the gradient of f is. Okay, so the gradient of f is equal to, so it's df by dx, df by dy, df by dz. Okay, so this is our kind of 3D derivative. Okay, and here df by dx is equal to, so we've got, so let's write this, yes, make it easier, x squared plus y squared plus z squared to the 1/2. Okay, so to differentiate this with respect to x, holding y and z constant, we get a 1/2, so 1/2, we get this bracket to the -1/2. So we've got a square root x squared plus y squared plus z squared. And then we have to differentiate what's inside the bracket, and we get 2x. Okay, so the 2x and the half cancel. And then we get the same thing for df by dy and df by dz, except we swap x for y. Okay, square root of x squared plus y squared plus z squared. And then we swap x for z in the last component. Okay, so the gradient of f in this case is equal to 1 over square root of x squared plus y squared plus z squared, x, y, z. Okay, fine. What about the gradient of a function, a scalar function that is the dot product between two vectors, where a is a constant vector? Okay, so let's think about a dot r. So a dot r is equal to a x, a y, a z, dotted with r, which is just x, y, z. Okay, so this is a x, x plus a y, y plus a z, z. Okay, and we want to take the gradient of this thing. Okay, which means we want to have the vector d by dx, d by dy, d by dz acting on this thing. Okay, so in the first component we've got d by dx of all of this. D by dx of all of this is just ax. Okay, because d by dx on these terms vanishes because we're holding y and z constant. D by dy just pulls out the ay, and d by dz just pulls out the az. Okay, and this is just nothing other than the vector a. Okay, so we found that the gradient of the dot product of a vector with the vector, the coordinate vector r, is just the vector itself. Okay, so far these are examples on scalar functions. So let me clean up and we'll look at how this directional, or how this 3D derivative acts on the vector functions. Okay, let's think about the vector a that is just the coordinate vector r. All right, so what can we do with the 3D derivative in this case? Okay, so how do we take derivatives of the vectors? Okay, so let's think about the divergence of a first. Okay, and we can write this with arrows. Okay, so the divergence of a is the scalar product you can think of d by dx, d by dy, d by dz of the vector a. Okay, ax, ay, az. Okay, and here our vector is just a coordinate vector, it's just x, y, z. Okay, so this is just d by dx, d by dy, d by dz, dotted with x, y, z, okay, which is just dx by dx is 1 plus, okay, so this is a dot product, So it's going to take two vectors and give us back a number. Okay, so it's this times this, okay, which is a differential d by dx acting on x, which is 1. This times this, so this is dy by dy, which is another 1, plus this times this, it's dz by dz, which is plus another 1. So this is equal to 3. Okay, so the divergence of r is 3. What about the other derivative? Okay, it's the curl of A. Okay, and remember the curl is given by, so we can think about the cross product of d by dx, d by dy by dz, with ax, ay, az. Okay, so this is daz by dy minus day by dz. And then that's the x component. The y component has d by dz of ax minus daz by dx. Okay, and the last component has day by dx, oops, minus dax by dy. Okay, so in this case where we've got r, it's just d by dy of az, which is z, minus dy by dz. That's the x component. And then we've got dx by dz minus dz by dx. And then finally, in the last component, we've got dy by dx minus dx by dy. Okay, and you'll note that all these partial derivatives give 0. So dz by dy means differentiate z holding, with respect to y, holding x and z constant. Okay, so this is 0. dy by dz holding x and y constant, 0. Okay, same with these. Okay, these are all 0. So the curl of A equals 0 in this case. So the curl of R, okay, so we're taking this example, equals 0. Okay, so the divergence of R equals 3, and the curl of R equals 0. Okay, and if we draw the vectors, so here's an xy plane, then at any point the vector field R represents a vector, okay, with magnitude R equals the square root of x squared plus y squared plus z squared. Okay, and it's a vector x, y, z, so it points like this. Okay, radially outwards. Okay, and if you look at these lines, they indicate that there's some kind of source. Okay, so there's something at the origin from which things are emanating. Okay, so divergence tells you about sources or sinks. Okay, if the divergence is positive, then you've got a source. Okay, so the arrows move away from the origin. If you've got a sink, then the arrows are reversed and things are going towards the origin. All right, so just like the electric charge case, if we put a positive charge here, the electric field lines go radially outwards from the origin. If you change the sign of the charge and make it a negative charge at the origin, then a positive charge is attracted towards that charge. Okay, so the field lines, the electric field lines of a negative charge will be the opposite way. Okay, and the divergence in that case will be -3 or less than 0. Okay, and the curl tells us about rotations, tells us about the amount of rotation. Okay, this clearly doesn't indicate any rotation. Okay, it doesn't look like anything like rotation here. Compared to previously where we looked at the water rotating, okay, where we saw that the lines were like this. Okay, there's clear rotation here. Okay, this was the case of rotating water. Okay, so in this case, the curl will not be 0. And maybe we'll look at that next, actually. Okay, so let me clear this up. And we'll keep going with a couple more examples. All right, so we just said about that water rotating example. So in that case, we had that V was minus By Bx 0. Okay, and we're asking what the curl. Okay, well, we can take the divergence of this first. So what's the divergence of V equal to? Okay, it equals d by dx, d by dy, d by dz. Okay, so you should be able to write this down, dotted with V, which is minus By Bx 0. Okay, so this equals, it's a dot product, so it's two vectors, scalar product is going to give us a number, and it gives us minus b dy by dx plus, so that's that, plus b dx by dy plus dz times 0. Okay. Now dy by dx is 0 and dx by dy is 0, so this is just 0. Okay, so in this case of the water rotating, the divergence is 0. Okay, there are no sources or sinks of anything. Okay, whereas in the electric field case, it's clear that there's some kind of source here, which the lines are emanating from. But what about the curl in this case? Okay, so I said the curl tells us about the amount of rotation. So in this case, we should expect something non-zero. But how do we calculate it? Okay, so remember what the curl is. Again, you should be able to write this down. Okay, I've asked what is the curl of a vector. You should be able to work that out. Okay, so let's think about the determinant form. So I'm going to write dx, dy, dz. Okay, and here I'm writing dy equals d by dy. Okay, just because I'm being lazy and I don't want to write d by dy all the time, or d by dx, d by dz. So I write it like this: vx, and vx is minus by, vy is bx, and vz is 0. Okay, so this is the curl of a vector. It's going to give us a vector. Okay, so the divergence gives us a number, okay, a scalar. This thing's going to give us a vector. Okay, so it's got 3 components, and the first component we find by covering up the first column and focusing on these things, and we get d by dz of bx, b times x. Then for the middle component, the j component, we cover the middle column up, okay, and we do d by dz of minus by, d by dz of by, and then for the last component, we cover this up and we do d by dx of bx minus, and it's a minus minus, so we get a plus, d by dy of by. Okay, now if you look closely, so b is a constant, remember? So dx by dz is 0, dy by dz is 0. Okay, so the first 2 components are both 0, and the final component of curl v is equal to, so b is a constant, so we can bring it out the front. So b dx by dx is just 1, plus b dy by dy. Okay, so this is equal to 2b 0, 0, 1. Okay, so in this case, curl v equals 2b 0, 0, 1. Okay, so this is a vector that points in the z direction that has magnitude 2 times b. Okay, so curl v tells you about the amount of rotation. Okay, and if b is larger, then the rotation will be faster. So curl v will be larger. Okay.